Yeah, welcome back after the short break, and we are discussing about the common collector amplifier, considering the resistance R C connected in the collector terminal in between collector and supply voltage V D D. So, let us see this circuit, which is the small signal equivalent circuit given here. The input voltage V in we are applying at the base, and then we do have the collector terminal, which is not AC ground, rather it may be having a signal called say V C. So, this is very important change compared to our previous analysis. We do have non-zero value of V C, and then rest of the things are same. Namely, at the emitter we are observing the the output current, output voltage VO. So, the VBE it is V in minus VO, as we have discussed before, and but then VC, if you see, once we have this output terminal is open, whatever the current it is flowing here, base current, that is flowing through this circuit, and finally, it is going to the ground here, because this current need to come back to the source through the ground. So, we can say that the current flow after reaching to the emitter, whether it is branching to the active device or through this R naught, finally, they are converging to the ground, and we can say that this is also same as the base current I B. So, if I call this is I B, this is also base current. So, if I B is flowing through this R C, the voltage getting developed here, it is we call V C. So, we can say that V C at this point with respect to ground is R C multiplied by I B. On the other hand, I B is V in minus V naught divided by R pi. So, what we can say that this V C equals to R C multiplied by I B, and I B it is V in minus V naught divided by R pi. So, this is what important thing, and that directly affects the current flow through this R naught. So, now if I apply KCL at the emitter node, what we are getting here, it is current flowing through this R O, which is V O minus V C divided by R naught. So, that is equal to the summation of the two currents, one is the base current, another is the through the active device. So, the base current is V in minus V naught divided by R pi, and the current flowing through this voltage dependent current source, it is G M into the V B, rather minus V B, going from it is basically coming here, V B. So, we do have V in minus V naught. So, summation of this current and this current, it is equal to this current. So, that is what we have written here. Now, this expression of this V C, it is in terms of V in and V O. So, this equation it can be utilized to replace this V C. As a result, we can get an expression which involves only V O and V in. Now, if we rearrange that equation, what we will be getting is V O multiplied by 1 plus G M into R naught plus R C divided by R pi plus R naught divided by R pi equals to V in multiplied by G M into R naught plus R C divided by R pi plus R naught divided by R pi. So, from this relationship between V naught and V in, that gives us the voltage gain. In fact, we can say that V O equals to V in multiplied by R C plus R O plus G M into R pi R O divided by R C plus R C plus R pi plus R O plus G M into R pi into R O. In fact, if you see here, this part it is common here and here. So, effectively you may say that the relationship between V in and V O, if I say, it is the impedance here which is R pi and the impedance of rest of the circuit there. Before we connect anything here, whatever the impedance we are having, it is R C plus R O plus G M into R pi into R O. So, this part is essentially the impedance at this point before we connect anything, of course, here. So, whatever it is, in this case again this part it is typically dominates, and so we can say compared to R pi, definitely this is higher because we do have G M into R naught multiplied by this R pi. So, we can say that this part you can ignore and this can be well approximated by 1. So, the voltage gain, even if we have say R C getting connected here and if we have say the V C voltage it is allowed to develop, then also the voltage gain it is close to 1. Now, let us see what will happen for the other parameters, namely the output resistance and then input capacitance and so on, and input resistance, right. So, we do have, let us move to the next slide to do that. So, let us concentrate on the input resistance, and here we do have the same small signal equivalent circuit. And for input resistance, what we have it is if we are applying V in here, whatever the I in it is flowing, if I get the expression of I in terms of V in, that gives us the corresponding input resistance. So, R in it is V in divided by I in, whereas I in it is the base terminal current, and base terminal current is V in minus V O divided by R pi. So, the expression of I in it is V in minus V O divided by R pi. Probably you can rearrange this equation, namely we can write in this form R pi divided by 1 minus V naught divided by V in. So, expression of this V naught by V in, which is the voltage gain, we already have seen that V O divided by V in is essentially this part. So, if I make 1 minus this part, what will be getting here in the denominator it is R pi will be getting here R pi, and then below of that we will be having this whole thing. So, I should say this whole factor 1 minus V O divided by V in, it is becoming R pi divided by the whole thing here, and this R pi and this R pi is getting cancelled, we can take this is in the numerator. So, as a result input resistance what we can get it is this only. So, here we are just summarizing that input resistance is R pi in series with R C, in series with R naught, and then the active device contribution. Again, because we do have this term coming in series, even though we do have this R C, this is also going to be very high. So, we can consider this is very high. It is quite obvious that since we are considering this resistance in series, it is increasing the overall resistance only by this part, and this part earlier we obtained that whatever the input impedance we are having. So, the effect of non-zero value of this R C, it is increasing this resistance even higher. So, anyway that is in our favor considering the required input port characteristic. So, so we have seen the voltage gain, we have seen the input resistance. Now, let us see the other parameter in the next slide. So, if you see the output resistance, so we do have the same small signal model, and to know the output resistance we have to make the signal is equal to 0, namely base terminal we are making it AC ground, we are stimulating the circuit with V x, and we are observing the corresponding current flowing through the circuit. So, what we have here, it is this I x, it is summation of all these currents. So, the current flowing through the device here, the whatever voltage dependent current source, it is G m into V b e, and incidentally V b e equals to minus V x. So, we can say that this current is G m into V x. And then we also have the current flowing through this device, and that device it is we do have say V x minus whatever the current flow we do have. Now, for simplicity what we have done is that since we are stimulating this terminal by V x directly, instead of considering this entire circuit and try to find what will be the impedance, we may split this part. One is this R pi part and then rest of the things. Now, if I get the impedance of this rest of these things, then the total output impedance it will be simply this output resistance coming from the encircled one in parallel with R pi. So, let us do this exercise considering only the encircled part. So, if we say that the current flowing through this this V x without considering this one, it is I x, then this current flow actually it is same through this R c. So, the current flow through this R c it is I x. So, the voltage here V c it is R c multiplied by I x. So, the current flow through this R naught it is V x here minus V c divided by R naught, and V c it is R c into I x. So, that it is a small small trick by which we can simplify the analysis. If you want, you can consider the entire circuit and you can find the output resistance, but if you do this one, it will be the analysis it will be simpler. Now, what we obtain here, it is the relationship between I x and V x, and from that we can get the ratio of V x divided by I x, that gives us V c plus R c plus R naught divided by 1 plus G m into R naught. So, interestingly, the resistance coming from this circuit, it is again it will be quite small. This part it may be dominating. So, we may approximate this by R c plus R naught divided by 1 plus G m into R naught. In later of our discussion in other circuits, we may come across the similar kind of circuit and try to remember this this part you may ignore. Try to remember this outcome of this analysis. So, there based on the value of this R c and then R naught, it may be in the order of 1 by G m, that may be the conclusion. Now, since we do have the R pi here, the total resistance, output resistance, it is the resistance coming from this encircled part and then R pi part. So, this is again you may consider this is R pi in parallel with R c plus R naught divided by G m into R naught. And if I say that this is this may be dominating over this R c, then you may approximate this by R pi in parallel with 1 by G m, which is again it can be said that 1 by G m it is dominating over R pi. So, the conclusion is that this output resistance in the order of 1 by g m, which is quote and unquote low. Okay. So, let us see the effect of this R C on the input capacitance. That is very tricky. So, in the next slide we will be analyzing the circuit to get the input capacitance. Yes. So, things are getting really getting complicated. Let us see what are the complications are getting here. So, we do have in the small signal equivalent circuit, we do have the C mu and then C pi. And note that compared to our previous discussion, the voltage here it is not AC ground, rather voltage it is VC, and VC it is of course, it is function of input voltage. Now, we may recall that the voltage at the output node VO, we already have this expression of this VO in terms of V in having this factor. So, numerator it is smaller than the denominator by this R pi, and then the expression of the VC it is the R C multiplied by whatever the current is flowing, and that is V in minus V O divided by R pi, that we have discussed before. This can be rearranged in this form. We can take V in outside, we are getting a factor 1 minus V O divided by V in. So, if I use the expression of V O in terms of V in, and if I plug in that expression here for V O divided by V in, what I will be getting here, it is this factor. In the numerator I will be having this part minus this part, and we will be having R pi in the numerator, and in the denominator whatever the things we do have here, it will be coming there. And the numerator, this R pi, it is getting cancelled here. So, what we have, it is in the numerator we do have R C and then V in, and then rest of the things in the denominator. So, the expression of the V C, it is V in terms of V in, it is V in multiplied by R C divided by R pi R C plus R naught plus G m into R pi into R naught. So, anyway, this is as expected, this is smaller than the input voltage. Note that we are not connecting any resistance here. The moment we connect the resistance here, the voltage here at the collector terminal, it is expected to be having much higher value, but right now we are not considering. If I consider R L is infinite here, earlier we consider R L. So, if I consider that, this gives an indication that V C it is a fraction of the V in. In fact, intuitively you can see that if this side is open, and if I start from the base terminal, and then if you go to the emitter terminal, then if you go to the collector, and then if you go to the ground, what we can see here, it is we are seeing one resistance R pi, here we do have one resistance R C, and also we do have this resistance R naught multiplied by 1 plus G m into R pi, that can be expanded in this form. So, from here to here, that is the impedance, and then the drop across this R C is the V C. So, you may say that V in it is getting potentially divided by this factor. So, that makes sense, this expression of this one makes sense. So, whatever it is, both R pi C pi and C mu are getting Miller affected. So, both C mu other terminal of the C mu, it is non AC ground, and of course, C pi it is also the other end, it is connected to V O, that is also non AC ground, right. They are having signals. So, the input capacitance at the base terminal, what we will be getting it is C pi multiplied by 1 minus gain from base to emitter, and let you call this is gain, it is AVE, and this AVE it is VO divided by V in. On the other hand, contribution of the C mu, it is C mu multiplied by 1 minus AVC, and what is AVC? We are defining this AVC by AC divided by V in. And we already have the expression of these two ratios, one it is from here, another it is from here. So, if you plug in those expressions and if we subtract from 1, the first part if you see what we will be getting here, it is the denominator, and if I compare denominator and numerator, we do have only r pi is the difference. So, in the first part what we will be getting is that C pi getting multiplied by r pi divided by the entire thing. So, likewise, when you consider the contribution of the C mu, and if I take this ratio getting subtracted from 1, what we will be getting here, it is except R C, which is here, rest of the things it will be there. So, that is why this C mu it is getting multiplied by this part, which is having R C, then R naught G m into R pi into R naught, and then denominator it is same as this one. So, you may say that this part, this factor it is approximately 1, whereas this part it is very small. So, approximately 0. So, we can say that the C in it is approximately equals to C mu for all practical purposes. So, again we are converging to the similar kind of conclusion, namely the input capacitance is low, input resistance of this circuit it is high, output resistance it is remaining low, voltage gain it is approximately remaining 1. So, we have done this analysis for a common collector circuit considering this collector resistance. Similar kind of things we can do for the MOS counterpart, and there instead of R C we may say that we may be connecting R D at the drain terminal, and this may be the corresponding MOS transistor, and we can do the similar analysis. And in the small signal equivalent circuit it will be very similar, except this corresponding R pi will not be there, or whatever the analysis so far we have done, that can be utilized judiciously by considering this R pi approaching to very high value. Okay. So, this is what you can share the analysis across different types of the circuit configuration, rather different types of circuit, namely analysis from common collector you can propagate to common drain. Note that it is not possible the other way, because in common drain circuit we do not consider this gate to source resistance. So, as a result, deriving the expression it will be for the common collector from the common drain, it is not possible. I should say rather analysis for common collector it is relatively generic, that can be extended for the common drain circuit. So, as I said that let us look into the common drain amplifier considering the resistance connected to the drain terminal. So, we do have this resistance connected to the drain terminal, and then we do have the R D coming in the small signal equivalent circuit, and then we do not have any R pi here. So, rather if I say that whatever the previous analysis we have done, if I consider the R pi in those equation approximately going to be very high, then we can get the equation for the common drain. So, let us start with the voltage gain and let us follow that approach. For common, so this is the equation we obtain for common collector circuit, and let us try to do for the common drain circuit, namely this circuit. So, if I say that expression of the VO can be obtained by considering this equation which we already have derived, and that can be done by making this is going to be very high, and this is going to be very high, and this is also going to be very high. Namely, in the numerator if I keep this term, and in the denominator if I keep this term and this term, and then if I pull out this r pi and if I cancel it, what we will be getting here, it is V in multiplied by G m into R naught in the numerator, and in the denominator we will be having 1 plus G m into R naught. So, from here directly we can say that the voltage gain, it is G m into R naught divided by 1 plus G m into R naught. Okay. Yeah. So, here this R d, I should say, on in the voltage gain, it is hardly having any effect, and again finally, we may approximate this by 1. Now, similar kind of things we can do for the output resistance. This part, let me clear. Yeah. So, if I consider say this part, earlier we have seen that if I want to know the resistance or impedance at the output terminal, and if I stimulate this circuit by a voltage source called V x, and then if I consider the corresponding I x, and then if I take the ratio of these two, that is supposed to be giving us the resistance coming from this circuit. And the previous analysis shows that the corresponding resistance is R c plus R naught divided by 1 plus G m into R naught. Now, this R c, instead of R c we can write R d for this case, and rest of the things it is same. Now, if I consider this part also, while you are considering this output resistance, of course, you have to make it ground, and since this R pi it is very high. So, this is very high. So, we can say that you can neglect this part and we can consider only this one. So, what we have, it is R naught or R out, it is R d, this is d, R d plus R naught divided by 1 plus G m into R naught, right. So, that is how we do get the expression of output resistance. Again, this is in the order of 1 by G m. Now, similarly, we can find what will be the input capacitance. Again, for this circuit, let me clear it up. Yeah. So, to get the input capacitance C in, we do have the contribution coming from C G S. Earlier, it was for common collector, it was C pi. So, we need to replace this by C G S. So, likewise here also we are having now it is C G D. Earlier in common collector circuit it was C mu. So, that need to be replaced by C G D, and then we do have the voltage gain from here to here. So, it should not be emitter, it is rather from gate to source and gate to drain. And this gate to source gain we already obtained here, which is given here, and we say that the corresponding voltage gain V o divided by V in, it was G m R naught divided by 1 plus G m into R naught, and so that gives us the corresponding ratio. Likewise, you can find what will be the this the A V d. So, that is V d, V d is the voltage here divided by V in, and if you plug in that expression, what you will be getting is that C in it is CGS multiplied by a factor like this, and then CGD multiplied by this factor. Now, whatever the factor we are writing here, here and here, of course, they are for common collector. To convert the equivalent factor for common drain, what you have to do, you have to make this term and this term dominating. So, likewise here also we can say that these terms are dominating. So, in this case what we will be getting is that C in it will be CGS multiplied by 1 divided by 1 plus Gm into R naught. So, let me write here C in equals to CGS multiplied by 1 divided by 1 plus Gm into R naught, and then CGD here CGD multiplied by we do have here Gm into R naught divided by 1 plus Gm into R naught. So, this part it is approaching to 0, this part it is approaching to 1. Okay. So, then we can say that C in it is approximately equal to CGD, right. Again this is quote and unquote low. This is approximately 1, output resistance is in the order of 1 by Gm, which is quote and unquote low. Input resistance of course remains high. So, then you can say that for common drain, even if I consider R d, then the basic required property of the buffer it remains the same. Now, so far we have considered either R d or R L here or maybe R s here. Now, if I consider maybe multiple elements together, things of course, it will be getting more and more complicated. You may try out to solve say this kind of circuits where we do consider say the RC part and then RL part. So, likewise we can consider RD and RL together, and then you can try to see what is the corresponding input resistance, voltage gain, and then input capacitance. Okay. So, I rather suggest you can work it out. In our numerical examples we will be covering. So, we may not be repeating the analysis again here, but in our numerical examples we will be discussing that. I think what we have it is, I think today let we conclude whatever the things we have covered so far. As I said that we are talking about common collector and common drain amplifier. Previous lecture we have discussed about this part, namely the seeing common collector and common drain as voltage mode buffer. Basic operation and biasing we just touched upon, and then we did the analysis for voltage gain and then impedance and then input capacitance for idealistic bias. And today what we have done it is we have done the analysis considering realistic components to get the voltage gain, impedance and input capacitances. Realistic components are the load resistance may be connected at the emitter or common or the source of the transistor respectively for BJT and MOS transistor, and then source resistance. Then also we have discussed about the effect of resistance at the collector terminal or drain terminal. What we are planning to go for the next class, it is numerical examples and some design guidelines. I think that is all I do have to cover. Thank you for listening.